All right, maybe a problem with washer. So with a washer, usually when you rotate the area, let's just see, for example, you rotate it around x-axis. All right, Aiden, go ahead. Yeah, okay. All right, let me just quickly make this example. Let's just see, we take this, this is a y equals 2x, this is a y equals x. Suppose that we want to take this region. Let's just see, this is doesn't matter, x equals 1, x equals 0. And we want to take that region, we're going to rotate it around x-axis. So rotate around x-axis. So if we do that, the product, the solid we get, obviously in the middle, when we sort of rotate the empty triangle in the middle, we get this cone shape, but that's empty, right? It's not there. And then the outside, if you take the sort of the largest triangle, the function y equals 2x, and to rotate around x-axis, you end up with this sort of big cone shape outside, right? So you get the solid outside, it's a cone, but inside it's also a cone, but inside the cone is missing, it's not there. So if you were to use sort of like a circular disc method, so you cut it vertically, so all the discs are vertically. So you have this shape in the middle. That disc has a thickness, right? Let's just say there's a small thickness there. If you put it on the side, it's really, that's the outside, the outer circle. And in the middle, you get an inner circle, and there's a thickness to this circular shape. So this is what we call a washer, right? Okay, yeah. So the volume of the solid is just a summation of the volume of all those. This is what we call washer. So the volume, total volume equals the integral of volume of one washer. This is what we call a washer. It's just it's something very similar to a disc. It's just that in the middle you have a sort of a disc being removed, right? So how do we find the volume of this washer? Well, we just take the cross-sectional area, the surface area, which is this part. So this is the cross-sectional surface area. So surface area times the thickness. In the past, I just wrote area. So that's what I meant, the cross-sectional area is the surface area of the washer. Now, how do we find the area? Well, the area is equal, well, the area, the surface has a small circle removed from a big circle. So the area will be just pi times the big circle. So the area of a bigger circle, so pi times r1 squared, where r1 being the radius of the bigger circle, minus pi r2 squared, where r2 being the radius of the small circle. The one in the middle, right? And then we can take out a pi, but we also have to figure out what R1 and R2 is in this case. So let's focus on the R1 and R2. I'm going to use a green. So R1, just going back to the solid we draw, that's the distance from the function y equals 2x to the x-axis. So R1 equals distance between the function y equals 2x and the x-axis. Well, it's a vertical distance, right? So you need to find the two y values and subtract in order to get the vertical distance. So here, the first one, we know the y, the highest y is 2x. Well, the second y is x-axis, so you have to turn it into y equals something, so that's y equals 0. So that's the lowest y value that will give you the biggest radius. So R1 will equal to 2x minus 0, it's just 2x. Now, what about the smaller radius? That is the distance from the function y equals x all the way to the axis of rotation, which is x-axis. So R2 equals distance between y equals x and the x-axis y equals 0. So we can write down R2 equals x minus 0, just x. So now we have two radius we can put in to find the area. So the area will be pi R1 2x squared minus R2 x squared. So that's the area, and we can put in there. But what is the thickness? Right? The thickness of that disk, the disk is vertical, so the thickness will be in the x direction. Right? So this part is what the thickness is. That's in the x direction, so we can call it delta x. In x. So in the integral form, so that will be dx. So volume equals integral pi 2x squared minus x squared, and then dx. And then the last thing we have to do is figure out the x boundaries. The lowest x, if we look at the shaded region, it begins from the origin, go all the way to x equals 1, that's given. So the boundary will be from 0 to 1. And I'm not going to finish solving it here. I'm just going to leave it the way it is. Find the integral of sine 11. All right, I can do that, Jason. But so this is a question someone was asking about washer earlier. Let me quickly take the same example, and I want to show you the shell method as well. Do it quickly. So suppose we still have this region, y equals x, y equals 2x, and this time I'm going to rotate it around y to create a solid. Try to do it quickly. So if you rotate around y, it's similar. You get this like a sort of cylindrical shape, but in the middle you get this cone being removed. Outside is sort of like a cone, but it's also like cylindrical shape. So this one I want to try to use the shell method. So if you recall that shell method, we have to think about like a cylindrical shells. So that means you have to find rectangle in the shaded region. When you rotate, you get a cylindrical shell. So in this example, if we take a small rectangle like this, and then we rotate that piece around, we get a cylindrical shell. Just show you that shape. Right, I might go back to that later, Sam. So that's a cylindrical shell. So the shell, the shell looks like this with a thickness. So that's a small thickness to the wall there. So the thickness is given by the base of the rectangle. Like I said, you have to decide which one to use, Chris. You can use the disk method. You can use the shell method here. I mean, the disk will be a washer method here. It's up to you. You decide which one to use. And then to use the shell method, you have to know the radius of the cylindrical shell and the height, as well as the thickness. So the volume will be given by the circumference of the cylindrical shell, 2 pi radius, times the height of the cylinder, times the thickness of that cylindrical shell, right? So that's the volume. And let's just figure out each one of them. The radius is here, so that's the radius. In the drawing there, this is the radius. Right? So the radius is the distance from the y-axis all the way to wherever that is. I don't know what that is, but I'm just going to call it x because there's a value on the x-axis. I'm going to call that x. So the radius is the distance between y-axis to the value, some x value, I'm going to call it x equals x. It's a horizontal distance that will give you the radius here. So what is the y-axis? That's x equals 0, and then the end of the radius is at some random x value, so x. So the radius is just equal to x minus 0, just x. So this part is the radius of the cylindrical shell. And what about the height? The height, this is the height of the cylindrical shell. So the height is equal to distance between the top function and the bottom function. The top function is y equals 2x, and the bottom function y equals x. Now, when we're looking for the height, we're looking for a vertical distance. So you have to take 2 y values to subtract. Yes, correct, Richard. No. So let me finish this. So the height is just going to be 2x minus x. So that will be the height. And what about the thickness? The thickness, this green segment, I know it's difficult to draw. The thickness is the base of the rectangle. That's in the x direction. That's what the thickness is. That's in the x direction, so that's delta x. In the integral, we just write dx. So now I can write down the volume. So I have 2 pi, radius we have is x, and the height we found out is 2x minus x. Obviously, you could simplify that if you like. And then the thickness will be dx. We rotate around the y-axis using the washer method. The thickness is the delta x. It's not dy, it's delta x. But if we use a disk method, or shell or washer method, not shell, disk or washer method, you slice the pieces horizontally if you rotate around the y, right? So you slice them horizontally, so the thickness is in the y direction there. So you have to look at the shape, the shape of the, either the disk, washer, or shell, and try to figure out the thickness from there. And then what's the boundary values? Well, it's dx, so we have to look for the x interval. So again, we keep the same, so from 0 to 1. So this is x equals 1. That's the shell method. Sam, yes, what you had is right, just to confirm. Okay, good. All right, so that's the volume. I'm not going to continue to integrate because I don't think they're too challenging here. You should be okay to integrate them. So that was another question by Jason.
I just have a quick question, if you don't mind answering it.
Mhm.
So does tangent squared of x always turn into secant squared of x minus 1? There's no other formula in integration by parts it turns into?
Correct. So yes. So that's just a trig identity. Tangent square x is always secant square x minus 1. That come from secant square x equals tangent square x plus 1. So both are equivalent. Jason had a question from a homework that's I'm integrating sine to the 11x cosine to the 6 power x dx. So this is when uses one of the tricks we talk about, right? Same and the Chloe, I guess. I'm not sure what you talk about. So this could be on it, right? Because this is 7.2. Yeah, this is 7.2 material. It could be on the exam. So if you recall that, well, problem like this, when you have sine and cosine multiplied, you have to look at the power. Here, sine is odd. So if sine is odd, we're going to save a sine and put it aside. So that will be integral sine to the 10th power x cosine to the 6x, and then the sine we saved, just put it aside, put it next to dx. And then we're going to rewrite the sine to the 10th and then write it as sine square x to the 5th power cosine to the 6th and the sine x dx. And the benefit of doing this is that we can rewrite sine squared using 1 minus cosine squared. So that's integrating 1 minus cosine square x to the 5th power. Is this really to the 11th power? That's brutal. Oh, wow. Cosine to the 6x, and then sine x dx. And then because we have a sine x dx, so the next step is we're going to let u equals cosine x du is equal to derivative of cosine is negative sine x dx. Move the negative, so you get negative du equals sine x dx, which we can substitute for the sine x dx directly. So now we get integrating 1 minus u squared to the 5th power cosine to the 6th, that's a u to the 6th power, and then du, negative. Obviously here we're not going to expand 1 minus u squared to the 5th power, just expand it, because that's just going to be, it's not impossible, you could still do it, but it's just gonna take a lot of time to expand it. And from here, it's probably better to use substitution again. I'm trying to think what's the best way to do it. Minus u, so can we let u equals 1 minus u squared. All right, I'm not going to finish this because I get stuck. I'm not sure if we should let u equals 1 minus u squared to do the u substitution, or let u just equal to u squared. One of those, you can do the substitution again, but it's going to take a while. I believe try this, that will work. or power reduction formula. I did not know this problem would take extra steps, but you will not need to use power reduction formula on the exam. The questions, if you have something like this, the power shouldn't be so high, so you don't have to worry too much about it. That's okay. So anyway, so we're just going to stop here. You're not going to have something with a higher power. But there was a question about what to do if the exponent were even. So if you have example that's sine to the even power, let's say sine to the, I'm going to pick a 2 x cosine 4x dx. This case, you're not going to save them, you're not going to save a sine or a cosine. So in this case, we're just going to use sine squared x equals 1/2 1 minus cosine 2x directly, and the cosine squared. Okay, good. It can be 1 minus something. Yeah, so try with the substitution if you want, if you have time later to play with. 1 plus cosine 2x. So anyway, so if you have both of them even power, so you're going to use those as the identities to rewrite them. You're not going to use the one I'm boxing in red. That identity doesn't work here. All right. So you're going to put in there, that will be integrating 1/2 1 minus cosine 2x, and then cosine to the 4th is cosine squared, so that's a 1/2 1 plus cosine 2x squared dx, and then you basically end up working with terms of cosine 2x. You have to be careful when you do the foiling or the expansion there. But you eventually turn them into, I'm going to do it quickly, so the 1/2 goes to the front. And then from the bracket term, you get 1/4 coming from 1/2 squared. And then you get 1 plus cosine squared. So that term, if you expand it, that becomes 1 plus 2 cosine 2x plus cosine squared 2x dx. And then you have to expand this entire expression by foiling. This is going to take a while. I'm not going to finish it. So that's just 1 minus, I think you end up with 1 minus cosine squared 2x, and then minus cosine plus a cosine 2x, and then minus a cosine cubed 2x. It just treat the cosine term as cosine x. So you're just integrating 1 dx, that should be okay. And then you integrate cosine squared 2x. Treat it as if you integrating cosine squared. Here, you have to use the cosine squared identity again. So that's integrating 1/2 1 plus cosine, instead of 2x, now it becomes 4x. That 4x is because we had a cosine squared 2x, right? So that's what we got. So you have to integrate each of this after using the identity. And the integrating cosine 2x dx, that should be manageable. And the integrating cosine cubed 2x dx, this term you have to rewrite it by writing as cosine squared. So now it's a power of cosine is odd, so you have to save a cosine. Because this is odd. This part, we do this because this is even. And from here, you're going to have to apply the identity that, not the one we use for the even case. You have to use 1 minus sine squared 2x times cosine 2x dx, and then let u equals sine 2x. This is like the case we did with the previous example when we have a sine with an odd power there. So when you have a cosine with the odd power, you do the same thing. But when they are even, you don't. So those are the even case. You have to use a different set of identity. Will this be on the exam? It could be, because this is section 7.2. Only the 7.3 material, when you have the square root, x squared, a squared, when you have that case, that will not be on the exam, because that's the 7.3. Okay, I talked too much. Let me make sure that I answer all the questions. So Sam was asking if we can finish the first example. I really don't want to finish it. I hate to disappoint you, but if you carry out what you did, I think that looks reasonable. Okay. Yes, just find the antiderivative, plug in values, you should be okay. I don't know, I just made up the example, so I don't know what the answer is. But like I said, I care more about the process, right? So don't worry too much about the final answer. Obviously, it would be great if you get all the final answer correct, but focus on the process if you when you work on those problems. Any other final questions? You don't have to stay on Zoom, just like the quizzes. You don't have to stay on Zoom, but I'll be on Zoom if you have questions. Again, like I said, just be honest, right? Show your own work. This is the time for you to demonstrate that you can answer those questions. Yeah, just do your best. Don't look up answers somewhere. If you have to use the decimals to graph, to plot functions, that's perfectly fine. Or if you have to use a calculator to plug in values, that's also okay. But don't just take the question and send it on the internet, have someone solve it for you. That's just not right. I'm sure you wouldn't do that, but just, show your own work, really.
Wait, one last question.
Yeah.
Before we start. Tangent squared of x is secant squared of x minus 1, or is it secant squared of x plus 1?
Right here.
Oh, it is plus 1. Oh, okay.
Okay. All right. Any other questions? All right. In that case, it's 6:39. So let's just assume that we start at 6:40. So I'm going to publish the quiz now, and I'll give you 1 hour and a half so that